Howdy guys. So today we're starting chapter 7. We're talking about VSEPR theory. So VSEPR theory, I'll explain what that means on the next slide. But first of all, we'll be examining the shapes of molecules with a general formula of ABX, where A is the central atom and B are the terminal atoms, which there could be 2 through 6 of them. Sometimes we might also use AXE notation, which you'll see on your homework, where A is the central atom again, but now X are the terminal atoms and E are the lone pairs on the central atom. So for example, for H2O, so oxygen is our central atom. So we've got a central atom, and then we've got 2 terminal atoms. So I should draw it down here. So we know that oxygen looks like this. We might not have drawn it this way yet, but you'll be drawing it this way pretty much all the time from now on, and you'll see why in the rest of this video. But water has 2 hydrogens, 2 terminal atoms, and then 2 lone pairs here as well. So it would be written as AX2, E2. So that's the AXE notation for water. I just gonna erase that box because I just drew over what I was writing. Anywho, back to the ABE note, or sorry, the AB notation. So AB notation for NH3. So NH3, our ammonia molecule, could be written as AB3, where N is the central atom A, and the 3 hydrogen atoms are the terminal atoms B. So there's 3 of them with the little subscript. So using this notation, we can describe lots of different molecules or polyatomic ions, and we can describe their shape all using this notation instead of each individual instance of whatever they are. So this table comes from your book where you can see some examples of AB2, AB3, AB4, AB5, and AB6. So we're going to see what all of these look like in their 3D geometries today. So now we're finally starting to talk about 3D geometries, which really, really influences the properties more so than what we saw with Lewis structures. For example, experiments can tell us that water has a bent shape. We're going to explore that more in the next video, so next time for Tuesday. But our experiments tell us that water has a bent shape. So the way I just drew it, like this, with the hydrogens at an angle and not straight out, like in our traditional Lewis structure. So our Lewis structure can be drawn linearly, but we know that water looks like this, not like this. So that tells us that, unfortunately, Lewis structures can't tell us everything. I love Lewis structures, they're great, I hope you love them too, but they can't tell us everything. So we get to learn some more exciting things called the VSEPR theory, where we get to learn that sometimes if we have 2 attached atoms, we can have a linear molecule or we can have a bent molecule. These are both AB2 molecules, but they have very different 3D shapes. Same thing when we have 3 terminal atoms, so our AB3, we can have very different molecular geometries here, so 3D geometries. We can have them all in a plane, like laying out like the spokes of a tire or spokes of a wheel. We can have them make a little pyramid, or we can have them in this T-shaped orientation. These are all valid 3D structures for AB3 molecules, and we will learn today how we determine what the 3D structure is from the Lewis structure and from the information we have about the molecule. So what does VSEPR mean? So VSEPR, VSEPR, stands for Valence Shell Electron Pair Repulsion Theory. It's a model for predicting the shapes of molecules in which electron pairs are arranged around each atom to minimize their repulsions. So remember, electrons are negatively charged, and anytime you have something that's negatively charged interacting with something else that's negatively charged, they're going to repel each other. So like charges repel, while opposite charges attract. So we want to minimize the electron-electron repulsions in our molecule. All right, so the positions around the central atom, we're going to learn a new term now. This term is electron domains. The positions around a central atom are occupied by electron domains. We use this term to encompass both non-bonding and bonding electrons around the central atom. So we use this term for a bond, so it doesn't matter what kind of bond, single, double, triple bond. No matter what kind of bond it is, it still only counts as one electron domain. One lone pair also counts as one electron domain. So let's see some examples of this. So down here, we're going to, this bottom row is going to be the total number of electron domains on the central atom in this molecule. So here's one example. So CO2, carbon dioxide, has 2 double bonds attached to its carbon. So we're always going to talk about the central atom, how many electron domains that central atom has. So carbon dioxide, that carbon has 2 double bonds around it, which corresponds with 2 electron domains. Doesn't matter that they're double bonds, it's still 2 electron domains. All right, what about ozone? So ozone over here looks very similar, at least in its Lewis structure, to CO2. We've got 1 double bond and 1 single bond, and there's also a little lone pair on that oxygen, that central oxygen. So our central atom has 1 single bond, 1 double bond, and 1 lone pair. So these are 2 different bonds, but it doesn't matter that one's a double bond and one's a single bond. They both count as single electron domains. So we have 1 single bond, it's 1 domain, 1 double bond, that's 2. Well, that's adding up to 2, so that's another electron domain, and then 1 lone pair, so that's a third. So we have 3 electron domains in ozone. What about ammonia? So our little ammonia molecule over here has 3 single bonds and a lone pair. So each single bond counts as 1 electron domain, and the lone pair counts as 1, so we have 4 electron domains. PCl5, so now we have 5 chlorines around our phosphorus atom. Those are 5 single bonds. Doesn't matter if they're single bonds or double bonds, right? But in this case, they're all single bonds. So that's 5 electron domains. There's 5 different bonds. And finally, our xenon tetrafluoride molecule might be a little hard to see, but there are 2 lone pairs on xenon, so I'll draw a little loop around them to emphasize them. So there's 4 single bonds, so 4 bonds to fluorines, different fluorine atoms, and there's 2 lone pairs also on xenon. So xenon's pretty big. It's down in period 5, I believe. Don't have my periodic table handy, but it's pretty big, so it can accommodate an expanded octet, and in this case it does. Oh, so does phosphorus, I guess. Should have noted that. But we have 4 single bonds and 2 lone pairs on xenon, so that's 4 electron domains, 1 for each single bond, and 2 electron domains, 1 for each lone pair, which adds up to 6 electron domains total. So once again, just keep in mind, doesn't matter what kind of bond it is, single, double, or triple bond, if there's one bond, no matter what kind, it counts as 1 electron domain. A different bond in the same molecule counts as another electron domain. So the number of bonds and lone pairs all added up gives us the number of electron domains. All right, and once again, we want to emphasize this theory is based on electron pair repulsion. So electron domains, whether they're bonding or non-bonding electrons, they're arranged to avoid one another as much as possible, or as best as possible. So let's take a look at methane. So methane is a really simple molecule. It so it's CH4, so it's carbon with 4 hydrogens, and this could be written in our formula of AB4, where carbon is our central atom A and hydrogen is our terminal atom B. All right, so in this case, we've got CH4. So CH4, each one of these bonds, so we have a bond, we have 4 single bonds from carbon to each of the different hydrogens. And those bonds contain electrons, of course. So in a single covalent bond, we have 2 electrons. So there's a pair of electrons in each of these bonds. And those electrons want to get as far away as possible from the electrons in the other bonds. And the optimal shape for this molecule, for that to happen, is called a tetrahedral shape. And that comes from the fact that if you draw a tetrahedron, so the 3D shape with 4 vertices, the smallest 3D shape you can have, well, the smallest number of edges you can have for a 3D shape, this is a tetrahedron. There's 4 triangles stuck together. The carbon is in the very middle of the tetrahedron, and the hydrogens make up the points of the tetrahedron. And we call this a tetrahedral molecule. So that is the electron domain geometry. So learning lots of new terms here, electron domain geometry for methane. And here is a demonstration using balloons of what these electron domain geometries look like. So if you use balloons, balloons actually represent the space taken up by electrons pretty well. So imagine there's 2 little electrons in each of these balloons, whether they're bonds or lone pairs. There's 2 little electrons in there. I guess if it's a multiple bond, there's more than 2. So keep that in mind for later. But for now, we'll just say there's 2. There's 2 little electrons in each of these balloons, and these are the optimal geometries to get them as far away from each other as possible. So here, they're going to be just in a straight line with the central atom keeping them apart. So the central atom is going to be where we have all our balloons tied together in the middle. You don't really see it, but that's that. And the electrons are as far away from each other as possible on opposite sides of that central atom. So this is a linear geometry. I'm not going to write them all out because I have them on the next slide. But in this case, we have 3 little electron pairs trying to get away from each other. So this is the optimal shape for that. So if we have a circle in 2D, then our circle is 360 degrees around. So to get as far away from each other as possible, we're going to be a third of that way around away from each other. So we're going to have 120 degrees between each of our electron pairs, and that's going to give us as much space as possible. Okay, here's our tetrahedron, like the CH4 molecule, our methane molecule. This is tetrahedron. These are as far away from each other as possible. So not just a flat cross shape. In a flat cross shape, we'd have 90 degrees away from each other. But in a tetrahedron, because of the additional degrees in the 3rd dimension, we can get 109.5 degrees away from each other, which is bigger and better for getting the electrons away from each other. This geometry is trigonal bipyramidal. So if we drew pyramids, so there's a little one in the back there, we could draw a trigonal pyramid. So the pyramid has 3 sides, and we could draw that pyramid on top and bottom. So that's why we call it a bipyramid or trigonal bipyramidal, because there's 2 pyramids. Bipyramidal means there's 2 of them, one on top and one on the bottom. So these electrons are as far away from each other as possible on top and on bottom, so they are on either sides of the central atom. And then we've got 3 around the middle that are taking this kind of shape. So we've basically got this shape vertically, and then this shape around the middle to make our trigonal bipyramidal shape. And finally, if we have 6 terminal atoms, we have all of our spaces occupied around, then we make an octahedron. Or if some of you are gamers, maybe you've seen an 8-sided dice before. This is an octahedron. It's got 8 sides. Um, and that is what makes it a, right? Yeah, and that, that is when we have 6 terminal atoms. We've got 6 vertices and 8 sides. But the sides don't really mean anything to us, just these vertices where our different electrons are residing as far away from each other as possible. Alrighty, so that is the beginning of the study, that is geometry. So electron domain geometry is the arrangement of the electron domains, all of them, whether they're lone pairs or bonds, around the central atom. Molecular geometry, on the other hand, or the actual 3D shape of the molecule, is the arrangement of the bonded atoms around the central atom. So just atoms, just bonds, not lone pairs when it comes to molecular geometry. When we're talking about molecular geometry, it's just the atoms. So you just kind of pretend that the lone pairs aren't there. You can't physically see them. If we had like a really strong microscope, we couldn't see them anyway. So we would see the molecular geometry. We'd see the shape of just the atoms if we looked at it with an electron microscope. All right. And this is a really nice table that shows you all the different shapes that are possible. So this column here, this first column, this is the ideal geometry. This is the electron domain geometry if all of the atoms, if all of the electron domains are bonded atoms. So we don't have any lone pairs. If that's the case, then we're in this column here. This column is for when we have one lone pair and all the rest are bonded atoms. This one is for 2 lone pairs and the rest are bonded atoms. And this is for 3 lone pairs with the rest being bonded atoms. And those are all the shapes that are possible. My personal favorite is the seesaw. So let's keep going. Alrighty, so the bond angle, I already mentioned a few different angles here when I was showing you the balloons, but the bond angle is the angle formed by 2 AB bonds with the central atom A at the vertex. So if you think of this red atom here, it's A, and these green atoms as B, for example, it's the, so this is the AB bond, this is the other AB bond, and it's the angle between those 2 bonds. That's our bond angle. So when we only have 2 electron domains, sorry, should not call them pairs, should call them domains. I missed that when I tried to update these slides. Imagine all of these say domains, not pairs. So we have 2 electron domains only. Then we have a linear geometry. There's no other option. They are going to be as far away from each other as possible, which is 180 degrees. So we're on opposite sides of this central atom. So we have 180 degree bond angles. These are ideal angles, and we'll talk about not really exceptions, but deviations in a little bit. But first, we're going to start with the ideal bond angles. Trigonal planar is when we have 3 electron domains, and those electron domains are all 120 degrees away from each other. So our bond angles are all 120 degrees. This is our tetrahedral molecule, like CH4. We have 4 electron domains and a tetrahedral shape. And I mentioned briefly that this angle between the bonds is 109.5 degrees. It's not 90 degrees, it's not flat like a cross shape. It is 3-dimensional, and it's 109.5 degrees of bond angles. our trigonal bipyramidal molecule down here, when we have 5 electron domains, we're going to have several different bond angles in here, actually. I should have one more written on here, technically. Oops. So the one between, so these, first I'll start by saying these two electrons are called axial. They're in the axial position. And these 3 around the center are in the equatorial position. So just like the equator of the Earth, it goes around the middle. So we have 3 equatorial electrons and 2 axial electrons. So between, or domains, I guess I should say. So between the axial electron domain and the equatorial electron domains, we have 90 degrees. It's a 90-degree angle. Between these 3 equatorial domains, on the other hand, we have 120 degrees. So they're just like a trigonal planar molecule around the middle. And then if we really want to take into consideration, if you look at the angle between the 2 axial positions, 2 axial electron domains, that's 180 degrees. And I'm going to erase all my lines because I made a mess. So yeah. All right. So we have 3 different possible bond angles in the trigonal bipyramidal. Up to now, we had the same between everything, but for the trigonal bipyramidal, we have 3 different bond angles. 90 degrees between the axial and equatorial, 120 degrees between the equatorial and equatorial, and 180 degrees between the axial and axial electron domains. And finally, if we have 6 electron domains, it's our octahedral molecule, as I said before. And all of the bond angles are 90 degrees, except if you look at any of the ones that are directly across from each other, of course. If you look at those are 180 degrees away from each other. But all of the axial, they're not really called axial and equatorial in the case of the octahedral molecule, but all of the adjacent, I guess I would say, adjacent bonds are 90 degrees. So we got 90 degrees everywhere in the octahedral molecule, which of course means that when we go to the next one, adjacent to that, it's 180 degrees. But that's what we're looking for. All right, so the steps for determining the electron pair geometry. First, we're going to start with the Lewis structure. So that's why we went over chapter 6. So that's why we spent so much time on Lewis structures, because we're going to use them a lot in this chapter as well. You draw your Lewis structure, you count the number of electron domains around the central atom. Remember, each lone pair counts as 1 electron domain, and any type of bond counts as 1 electron domain. So single, double, triple bonds, doesn't matter. They're all 1 electron domain. And then a different single, double, triple bond, whatever, is a second electron domain. So we count the number of electron domains around the central atom, and then we use that number of electron domains to determine the ideal geometries, those 5 that I just told you: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Those are our ideal geometries. All right, so that's how we determine the electron domain geometry. But like I said before, that counts for everything. That counts for the lone pairs and the bonds. When we only care about the bonded atoms, when we care about the things that we could see if we looked at it under an electron microscope, now we're talking about the molecular geometry, or the shape. We're talking about the arrangement of the bonded atoms only. We're not talking about lone pairs anymore. So lone pairs are out around the central atom. There are many molecules for which the shape is not the same as the electron pair geometry. So for example, there are some where it is the case, like CH4, that tetrahedral molecule. It has a tetrahedral electron domain geometry and a tetrahedral molecular geometry because it doesn't have any lone pairs. So when we do have lone pairs, that should be domain. When we do have lone pairs, then the electron domain geometry is different from the molecular geometry. So for example, here's an example where they're different. Ozone, we've seen ozone a few times now, O3, has a trigonal planar electron pair or electron domain geometry. We'll often use either term sometimes, and a bent shape. So this is the shape. This is what we see if we were to look under an electron microscope. But there are two lone pairs here. So see them over here on the Lewis structure? There are two lone pairs there, which gives us the trigonal planar electron domain geometry, but we pretend they're not there. We ignore them when we look at the shape. So it's a bent shape. Alrighty. So what other examples do we have here? So like I said, CH4 is a tetrahedral geometry. It's got a tetrahedral electron domain geometry and a tetrahedral molecular geometry. It's the same. So those are 109.5 degree angles in our tetrahedron. NH3, so this is ammonia. If we drew the Lewis structure for ammonia, we'd see that nitrogen has a lone pair on it, which makes up the octet for nitrogen. So that lone pair doesn't count in the shape when we talk about the molecular geometry. So you can see it here hanging out where we start with a tetrahedral geometry like this. And we then ignore the lone pair and we see this trigonal pyramidal. So not trigonal bipyramidal, but trigonal pyramidal. We got a tiny little pyramid here. That is the shape for ammonia. All right, what about water? So water, I like to draw it like this, and you'll soon like to draw it like this too. This is the Lewis structure for water. It has two lone pairs, which gives water a bent shape. So you can see that those lone pairs were on here, which is why we started with a tetrahedral shape. But if we ignore them and just look at the molecular geometry, it's a bent molecule. So that's why we say water is bent. And what happens is that when we add lone pairs, so not just we have a different molecular geometry than electron domain geometry, we also change the bond angles. They get slightly smaller than 109.5. When we added one lone pair to ammonia, we change the bond angle to 107.5. We add another one to our water molecule, and our bond angle decreases even more to 104.5 degrees. So that's because lone pairs occupy more space around a central atom than bonding pairs. There are other deviations as well from these ideal bond angles. So here's the one for ammonia again. We also have a deviation when we draw this little molecule. So this guy is formaldehyde. You don't need to know that, but this is formaldehyde, and it appears to have a trigonal planar shape, but this angle between the oxygen and so the carbon-oxygen bond and the carbon-hydrogen bonds is bigger than 122, or bigger than 120. And the angle between the carbon-hydrogen bonds is smaller than 120. And that's because it's a double bond here. This double bond, while it still counts as only one electron domain, the double bond does repel more strongly because there are 4 electrons in there instead of 2. So those 4 electrons are repelling more strongly the other 2 electron domains. So they get closer together while getting further away from the carbon-oxygen double bond. All right, so SF4 is actually it's actually a seesaw shape. sorry, I forgot what my favorite shape was called for a second there. It's got one lone pair on the sulfur. Sulfur has an expanded octet. And instead of having these two axial fluorines being 180 degrees away from each other, they're actually 173.1, so they're a little bit less because this lone pair is taking up all the room, just like the lone pair on ammonia, making that bond angle smaller. It also makes this bond angle smaller between the equatorial fluorines, so that bond angle decreases to 101.5 instead of 120 degrees, whereas this one decreased from 180 to 173. And then bromine pentafluoride, this one is what we call a square pyramidal shape. It's got a lone pair down here. And instead of having all 90-degree angles, which it would from its octahedral geometry, the electron domain geometry, instead of having all 90-degree angles, it has 84.8. And that is because those lone pairs occupy more space than bonding pairs. And just to finish up here, we can also have molecular geometries in molecules with more than one central atom. So what does that look like? So this is a little organic molecule called methanol, where we have two central atoms. So the carbon has things attached to it. The oxygen also has things attached to it. So they are both central atoms. So we have a molecular geometry about the carbon atom. That's how we phrase it, or around the carbon atom. And we have a molecular geometry around the oxygen atom. In this case, they're both tetrahedral because there's a hydrogen, 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 and oxygen around the carbon, which makes it tetrahedral. It's got 4 electron domains. And then if we look at the oxygen, it's got a carbon, a hydrogen, and 2 lone pairs. So 4 electron domains. It has a tetrahedral electron domain geometry as well. I'm going to erase some of that because it's messy. But the molecular geometry is not the same. So the molecular geometry around this one, around the carbon, is tetrahedral because all 4 of those things that are attached, all 4 of the electron domains are bonds. They're bonded atoms. So the bond angle is about 109.5 degrees. It's pretty ideal. Whereas this oxygen, so the carbon-oxygen bond, compared to the oxygen-hydrogen bond, that bond angle is going to be less than 109.5. And we know that because this is actually a bent shape. So this is actually kind of, we're not going to draw it like this because that would be silly, but this is what the 3D geometry actually looks like, where we have these lone pairs giving it a bent shape, kind of like water. So just imagine that this is hydrogen instead of a CH3 group. If this is just a hydrogen, then it's just water. So it's a bent molecule. So the bond angle is going to be less than 109.5 because of the lone pairs pushing everything out of the way. All right, finally, I'm not going to go over this, but these are the steps to determine the molecular shape. You start with the first 3 steps where you determine the electron geometry. Those 3 steps I had on the previous slide. And then the last 3 steps are taking the electron domain geometry and ignoring the lone pairs to determine the molecular shape and the ideal bond angles. And this summary you can use however you need, but you should commit these steps to memory, which you don't have to actually memorize these steps, but you have to practice them. So use these steps the first few times you try to determine molecular shape, and then you'll get used to it and you won't need to know what the actual steps are anymore. But these are a guide for you. And then this little table tells you what all the different molecular geometries are called. We got them all here, even seesaw, my fave. All right, so this is just a summary table for you. Refer to this as needed. And I will see you guys tomorrow.